Back with structure and interpretation of computer programs. Let me take the PDF. Okay. Greatest common divisors. The greatest common divisor, GCD, of two integers a and b is defined to be the largest integer that divides both a and b with no remainder. For example, the GCD of 16 and 28 is 4. In chapter 2, when we investigate how to implement rational number arithmetic, we will need to be able to compute GCDs in order to reduce rational numbers to lowest terms. To reduce a rational number to lowest terms, we must divide both the numerator and the denominator by their GCD. For example, 16 divided by 28 reduces to 4 divided by 7. One way to find the GCD of two integers is to factor them and search for common factors, but there is a famous algorithm that is much more efficient. The idea of the algorithm is based on the observation that if R is the remainder when A is divided by B, then the common divisor of A and B are precisely the same as the common divisors of B and R. Thus, we can use the equation saying that the greatest common divisor of A and B is the same great common divisor of B and R. To successively reduce the problem of computing to a GCD to the problem of computing the GCD of smaller and smaller pairs of integers. For example, here we have the example of GCD of the pair 206 and 40, and we can see how the number 2 is found through a couple of iterations, or I should say recursions. Because basically GCD of 206 and 40 can be reduced to the GCD of 2 and 0, which is 2. It is possible to show that starting with any two positive integers and performing repeated reductions will always eventually produce a pair where the second number is 0. Then the GCD is the other number in the pair. This method for computing the GCD is known as Euclid algorithm. It is easy to express Euclid algorithm as a procedure. Yes, this is very straightforward, very easy. This generates an iterative process whose number of steps grows as the logarithm of the numbers involved. Yes, I can see why, because basically every time you are dividing. The fact that the number of steps required by Euclid's algorithm has logarithmic growth bears with an interesting relation to the Fibonacci numbers. And I guess that this relation is the Lamé's theorem. If Euclid's algorithm requires k steps to compute the GCD of some pair, then the smaller number in the pair must be greater than or equal to the kth Fibonacci number. Let me reread again. Euclid's algorithm requires k steps to compute the GCD of some pair. Okay, then the smaller number in the pair must be greater than or equal to the kth Fibonacci number. Okay. And we can use this theorem to get an order of growth estimate for Euclid's algorithm. Let n be the smaller of the two inputs of the procedure. If the process takes k steps, then we must have n greater or equal to the kth Fibonacci number, which can be approximated by phi to the power of k divided by the square root of 5. Therefore, the number of steps k grows as the logarithm to the base phi of n. Hence, the order of growth is theta log n. I see. I don't want to read this long footnote. Here we have an exercise. Let me read it. The process that a procedure generates is, of course, dependent on the rules used by the interpreter. As an example, consider the iterative GCD procedure given above. Suppose we were to interpret this procedure using normal order evaluation, as discussed previously. Using the substitution model, okay, I don't think I want to do this exercise. Example, testing for primality. This section describes two methods for checking the primality of an integer n, one with the in order of growth theta square root of n, and a probabilistic algorithm with order of growth log n. The exercises at the end of this section suggest programming projects based on these algorithms. Okay, searching for divisors. Since ancient times, mathematicians have been fascinated by problems concerning prime numbers, and many people have worked on the problem of determining ways to test if numbers are prime. One way to test if a number is prime is to find the number's divisors. The following program finds the smallest integral divisor greater than 1 of a given number n. It does this in a straightforward way by testing n for divisibility by successive integers starting with 2. Let's see, so here we have a definition, smallest divisor takes an argument n and calls the procedure find divisor that wants two arguments n and 2. Here we have the definition of find divisor. We have these conditional procedures. Okay, this is simply the definition plus an helper procedure divides that check this procedure basically is checking if B is a perfect divisor of A. We can test whether a number is prime as follows. N is prime if and only if n is its own smallest divisor. Okay, the n test for find divisor is based on the fact that if n is not prime, it must have a divisor less than or equal to the square root of n. This means that the algorithm need only test divisors between 1 and square root of n. Consequently, the number of steps required to identify n as prime will have order of growth square root of n. Okay. 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 The Fermat test, the log n primality test is based on a result from number theory known as Fermat's little theorem. I know nothing about this stuff. Fermat's little theorem: if n is a prime number and a is any positive integer less than n, then a raised to the nth power is congruent to a modulo n. If n is a prime number and a is any positive integer less than n, then a raised to the n power is congruent to a modulo n. I don't know what... Okay, it is explained right below. Two numbers are said to be congruent modulo n if they both have the same remainder when divided by n. Okay. I see. The remainder of a number a when divided by n is also referred to as the remainder of a modulo n, or simply as a modulo n. If n is not prime, then in general most of the numbers a less smaller than n will not satisfy the above relation. This leads to the following algorithm for testing primality. Given a number n, pick a random number a less than n and compute the remainder of a to the power of n modulo n. If the result is not equal to a, then n is certainly not prime. If it is a, then chances are good that n is prime. Now pick another random number a and test it with the same method. If it also satisfies the equation, then we can be even more confident that n is prime. Yes. By trying more and more values of a, we can increase our confidence in the result. This algorithm is known as the Fermat test. To implement the Fermat test, we need a procedure that computes the exponential of a number modulo another number. So this exp mod. And you need the base, you need the exponent, and you need m. Okay. Yes, indeed. This is very similar to the fastExp procedure that we have seen previously. It uses successive squaring so that the number of steps grows logarithmically with the exponent. The Fermat test is performed by choosing at random a number a between 1 and n minus 1, inclusive, and checking whether the remainder modulo n of the nth power of a is equal to a. The random number a is chosen using the procedure random, which we assume is included as a primitive in scheme. Random returns a non-negative integer less than its integer input. Hence, to obtain a random number between 1 and n minus 1, we call random with an input of n minus 1 and add 1 to the result. This is very clear, very easy. The following procedure runs the test a given number of times as specified by a parameter. Its value is true if the test succeeds every time and false otherwise. Okay, this is just a lot of number theory and mathematics. I don't see any computer science concepts here, so I'm going very fast. Okay, this was just an example. Okay, vabbè. Cool. Probabilistic methods. The Fermat test differs in character from most familiar algorithms, in which one computes an answer that is guaranteed to be correct. Here, the answer obtained is only probably correct. More precisely, if n ever fails the Fermat test, we can be certain that n is not prime. But the fact that n passes the test, while an extremely strong indication, is still not a guarantee that n is prime. What we would like to say is that for any number n, if we perform the test enough times and find that n always passes the test, then the probability of an error in our primality test can be made as small as we like. Sounds good? Unfortunately, this assertion is not quite correct. There do exist numbers that fool the Fermat test. Numbers n that are not prime and yet have the property that a to the power of n is congruent to a modulo n for all integers a less than n. Such numbers are extremely rare, so the Fermat test is quite reliable in practice. There are variations of the Fermat test that cannot be fooled. In these tests, as with the Fermat method, one tests the primality of an integer n by choosing a random integer a smaller than n and checking some condition that depends upon n and a. See exercise 1.28 for an example of such a test. On the other hand, in contrast to the Fermat test, one can prove that for any n, the condition does not hold for most of the integers a less than n unless n is prime. Thus, if n passes the test for some random choice of a, the chances are better than even that n is prime. Let me reread this passage. If n passes the test for some random choice of a, the chances are better than even that n is prime. The chances are better than even. If n passes the test for two random choices of a, the chances are better than 3 out of 4 that n is prime. By running the test with more and more randomly chosen values of a, we can make the probability of error as small as we like. The existence of tests for which one can prove that the chance of error becomes arbitrarily small has sparked interest in algorithms for this type, which have come to be known as probabilistic algorithms. There is a great deal of research activity in this area, and probabilistic algorithms have been fruitfully applied to many fields. And we have a bunch of exercises. Let's see. Exercise 1.21 doesn't seem to be particularly interesting because it's just an application of a procedure. Exercise 1.22. Okay. Not sure I want to do these exercises because there is a lot of math and I'm not a great fan of this kind of math. Prime numbers, more in general, number theory. I don't like this kind of math. So if there is something more related to computer science, I will be happy to do the exercise. Otherwise, I will skip these exercises. Maybe the 1.26 is interesting because it's about optimization and is about a glitch in the definition of a procedure that makes the algorithm run significantly slower than the correct version of it. 1.27 is math. Okay. I think I will stop here. We are left with this 1.3 paragraph formulating abstractions with high order procedures. Let me check. Okay, we are here. We have four more sub paragraphs and okay, I will stop here, and in the next video I will go through these formulating abstractions with high order procedures. So see you in the next video. Ciao.